In this lesson, we are going to learn a new system called polar coordinates that can be used to describe points in the plane. The system that you currently are the most familiar with is called the Cartesian coordinate system. And in that system, you're given an x and y coordinate. And the x coordinate determines how far over you go, and the y-coordinate determines how far up or down, and that is your point in this Cartesian system. What we will do with polar coordinates will be a little bit different. We're going to fix a point called the origin and fix a ray. And we're going to describe points as a certain angle of rotation and a certain distance out. So to define a polar coordinate, you fix a point O called the pole or the origin. And you can put that on what the normal origin is in the Cartesian plane if you want to talk about superimposing these two. And you construct a ray from O called the polar axis. So the polar axis is sort of the same thing as the x-axis in this case. And each point P is assigned polar coordinates r, theta, where r is the directed distance from O to P. So we will deal with things where that r is negative, and we'll get to how you deal with that in a second. And theta is the directed angle measured counterclockwise. So as in an angle of pi thirds means go counterclockwise pi thirds from the polar axis to that segment. And then this is the point we're looking at. So the system will be different. We'll be able to use this system to graph some pretty interesting looking curves and things. So first let's get familiar with it. So plot these polar points. So the point 3, 3 pi quarters, the r is equal to 3, the theta is 3 pi quarters. So we go a distance of 3 out from the origin. So this is my origin, and there's 1, 2, 3 away is that point right there. And then we take that ray and we rotate it 3 pi quarters, which puts us around to here. So that's where the point 3 pi quarters is. It's been rotated 3 pi quarters from the original position, and the distance from the origin to the point is 3. And these little circles are all the points that are distance of 1 away, all the points that are distance of 2 away, etc. It just makes graphing these points a bit easier. So the point 2, 3 pi means go 2 away from the origin, and then rotate 3 pi. Well, one full rotation is 2 pi, and then another half a rotation puts us right there. So that's the point we're looking at. So this one's a little bit funky. You have the point where r is -4, and theta is -5 pi 6. And you ask yourself, what could that r being negative mean? You can't really think about it in a radius in that sense. So here is how you graph points with negative radii. You start by graphing the point 4, -5 pi 6 with that r being positive. So there's a distance of 4 out, 1, 2, 3, 4. And backwards 5 pi 6 puts us right here. And to account for the negative, you reflect over the pole. So reflect over pole, meaning that point that we have that's right here, it reflects to there. And that is how you plot points that have negative radii. Plot the point with the positive radius using the same angle, and the -5 pi 6 just meant go clockwise instead of counterclockwise. And then after you've done that, reflect, and that's where your point is with that negative radius. Now in the Cartesian system, the representation of points is unique, meaning if you and a friend plot a point xy and your x's and y's are the same, you're going to get the same point. And the question is that true for polar curve? Let's graph the following points and we'll see if it's true. So the point 2, pi quarters says go out 2 and rotate pi quarters, giving us this point right there. The point -2, 5 pi quarters Remember, we start by plotting the point 2 5 pi quarters. So that's 2 out, 5 pi quarters throws us right there. And then that point reflects up. And it looks to me like it's in the same place as the previous point in example A, and that is not incorrect, that is right. Similarly, let's try that a different way. -2, -3 pi quarters. Well, we'll start by plotting 2 -3 pi quarters. So we go out 2 and then backwards 3 pi quarters, and then reflect up. And there you go. So we have 3 different representations that all gave us the same point. So that answers the question, is this representation unique? The answer is no. There are many different ways to represent one point. In this system. Now, as this system is also plotting points in a plane, there must be sort of some way to go back and forth between them. Say you know an r and a theta, and you want to know what that is in x and y, and vice versa. So to convert from polar to rectangular, you use the fact that x is r cosine theta and y is r sine theta. And the question is well, why is that true? So let's consider a point r theta in quadrant 1. So it's a distance of r away and angle of theta. And if that point were plotted using x and y, this would be the x, this would be the y. Now, the thing to notice is that sine of theta is y over r, and cosine of theta equals x over r. And notice that if you isolate y and isolate x in those equations, that gives you back these equations. So from rectangular to polar is a little bit more tricky. You can see that this r squared equals x squared plus y squared that comes from that triangle in the Pythagorean theorem. And then tangent of the angle that you have will give you x over y. So if you knew the x and y, you could look for the value of tangent that gave you that angle. You just gotta be a little bit careful because using inverse tangent won't always work because that has a restricted domain. You'll have to watch out as to which quadrant you're in. All right, let's use those conversion formulas to convert the following points from polar to Cartesian or rectangular coordinates. So first, let's plot the point. We have our origin and our polar axis. We are a distance of 2 away and an angle of pi 6. So call that 1, call that 2, and this angle in there is theta equals pi 6. So to convert that point into Cartesian coordinates, we know that x is r cosine theta. So x will equal 2 times cosine of pi 6, and cosine of pi 6 is root 3 over 2. So x would equal root 3. So that distance is root 3. And y is r sine theta. So the y is 2 times sine of pi 6. And sine of pi 6 is 1/2. So 2 times 1/2 gives us 1. So in the rectangular coordinate system, this is the point radical 3, 1. So 1 -3 pi quarters. If that's my origin, here's my polar axis, a distance of 1 away, and I rotate backwards 3 pi quarters. So roughly speaking, there's your point. This is 1, this is an angle of -3 pi fourths. So we should theoretically have an x value that is negative in this case and a y value that is negative in that case, because if this were plotted in the Cartesian system, that would fall in quadrant 3. So let's see if that checks out. X is r cosine of theta, so x is 1 times cosine of negative 3 pi quarters. Well, cosine of negative 3 pi quarters is negative root 2 over 2. And y is equal to r sine of theta. So 1 times sine of negative 3 pi quarters. And at negative 3 pi quarters, the sine is also negative root 2 over 2. So this point in Cartesian coordinates is negative root 2 over 2, negative root 2 over 2. Okay, so let's convert the following points into polar coordinates. So first it helps to plot the point. So the point that we're looking at is negative 1, negative 1. So back 1, down 1, there's our point. So we need to find the r, and we need to find the theta. So r is the distance from the origin to that point. And to find that, we use the Pythagorean theorem, which says that x squared plus y squared equals r squared. So negative 1 squared plus negative 1 squared is r squared. R squared is 2. And so r is technically plus or minus root 2, but let's just use positive root 2 because it's easier. And you can find this angle, the angle, a few ways. We can use the fact that tangent of theta will have to equal y over x, or negative 1 over negative 1. So tan theta must equal 1. And the other thing is it must put you into quadrant 3. So tangent of theta is 1 at pi quarters, but that doesn't put you into quadrant 3. The angle that you need here is 5 pi quarters. So one way to express this point could be root 2, 5 pi quarters. This representation is not unique, so that is not the only way. You could have also said root 2, negative 3 pi quarters. And instead of going counterclockwise with that angle, you would go clockwise. If you would like to be really, really clever, you could have said negative root 2, positive pi quarters. Because to plot that point, you would go forwards pi quarters with a distance of root 2, and then you would reflect down. So with these, if you want to make my life difficult, you can get clever and you can all give me different answers, and I've got to figure out if they're right. But it is the case that this first one that we gave is sort of the easiest one to visualize, I believe. All right, how about the point 0, 3? So in the Cartesian system, the point 0, 3 is over nothing and up 3. And there it really isn't even necessary to use the Pythagorean theorem to figure out what the r is, because it's pretty obvious that that point is 3 away from the origin. It also is pretty obvious what the angle is. The angle from our polar axis to that point is pi halves. So one representation is 3 comma pi halves. Another one could be negative 3 pi halves. And the really clever one, you could use, say, negative 3 negative pi halves. That would do it. That puts you down here, and then you would reflect up. So any of these answers is correct. All right, sketch the region in the plane that consists of points whose polar coordinates satisfy the given conditions. So the first thing is that r is bigger than or equal to 0, so positive radii, and the angles are between pi quarters and 3 pi quarters inclusive. So pi quarters is this ray here, and since I have an or equal to on the boundary, that will be a solid line. 3 pi quarters is over here, and r being bigger than 0 means we want all the things that are a positive distance away from the origin within these angles, and that's all this stuff here. So everything within that region is what we're looking for. Extending, of course, out to infinity. All right, next we have a radii between 1 and 3, an angle between pi and 2 pi. Okay, so here is the angle pi, here is the angle 2 pi. We want everything between those angles, including them that are a distance of between 1 and 3 from the origin. So there's the boundary of all the points that are a distance of 1 away. There's the boundary of all the points that are a distance of 3 away. And we want all of the points in between, inclusive of the ends. So that's the part we're looking at. And it's a solid, all the lines on the edges are solid because we have or equal to signs on the inequalities. Had those had less thans or greater thans without the or equal to, then you would need a dotted line on the boundary. But there's all the points that are a distance of between 1 and 3 from the origin, and an angle of 0 and pi and 2 pi from the polar axis. The next thing we will do is look at how the representation of functions can look quite different in this polar system versus the Cartesian system. So the question is in the polar system, what would r equals 2 secant of theta look like? And it turns out that this is a pretty simple equation in the Cartesian system. First, you notice that r is 2 times 1 over cosine of theta, since secant is 1 over cosine. Multiply the cosine over, and r cosine of theta equals 2. And if you look at our conversion formulas, r cosine theta, well, that's actually just x. So r equals 2 secant theta is a vertical line of x equals 2. And so that one was pretty obvious. You can figure that out pretty easily by converting the secant into cosines and using the fact that x is r cosine theta and y is r sine theta. That's one way. This next one, you got to think about, what does it mean to be theta equals pi thirds? Well, that means all the points, any r, that are an angle of pi thirds from the polar axis. So obviously all the points on that side. And then the question is, that's for all the radii that are positive or even 0, because 0 would be the point going through the origin. Now the question is, what if you had a negative radius? So what if you had r less than 0? Well, in that case, let's just suppose that r was equal to negative 2. And if you had to plot the point negative 2 pi thirds, you would, say, go a distance of 2 away, up pi thirds, and then you would reflect over the pole down. And doing that for all the points that have negative r is going to give you that half of the line as well. So this is a line. It passes through the origin 0, 0. What we're going to need to do is to find the slope of that line, finding one more point that it passes through. Well, you can use the fact that if this distance is 1, then you have a point on the unit circle. And in that unit circle, this coordinate is now 1/2. This coordinate is root 3 over 2. So you also have a point 1/2 root 3 over 2, which will allow you to find the slope. So the slope will be root 3 over 2 minus 0 over 1/2 minus 0. Turns out that's just root 3. The equation of the line, y minus y1, is mx minus x1. So that's y minus 0 equals root 3 times x minus 0, or y equals root 3x. So the only potentially tricky part about that equation really is the fact that it has sort of a funky slope. All right, r equals 5. So just think about what this means. This is all the points that are a distance of 5 from the origin. That should sound awfully familiar. That is the definition of a circle with r equals 5 centered at the point 0, 0. And here's how you can prove to yourself that that's true. If r equals 5, r squared is 25. And we know that r squared is x squared plus y squared. So that is indeed a circle with radius 5 and center at the origin. All right, tan theta, secant theta. It's not immediately obvious what this is, but we can think about tangent as sine theta over cosine theta. We can think about secant as 1 over cosine theta. So we can think about this as r equals sine theta over cosine squared theta. And so then r times cosine squared theta equals sine theta. And then we have r cosine theta times another cosine theta equals sine theta. And you can immediately see that this r cosine theta, you could replace that by x. But both the cosine and the sine theta would need an r to do that. So how you can accomplish that is this. You multiply this side by r, multiply that side by r. And that will give us r cosine theta times r cosine of theta equals r sine theta. And on the left side, we just have x times x, or x squared. On the right side, we have y. So this curve in Cartesian coordinates is the curve y equals x squared. And you might ask yourself, well, what good is this system if all we can do is, all we've done so far is get equations for things we can already deal with in the Cartesian system? And the answer comes with the next questions. We're going to actually graph some curves in the polar coordinate system. So a useful technique to graph this polar curve r equals 4 sine theta is to first sketch the graph in Cartesian coordinates. All right, so the sine function goes through one oscillation in 2 pi, or that's the period of the sine function. And in this case, the amplitude of my sine function is 4. 1, 2, 3, 4. Okay, halfway to 2 pi is pi, halfway to pi is pi halves, and halfway between pi and 2 pi is 3 pi halves. All right, so the sine theta equation starts at 0, 0. By pi halves, we're up to 4. By pi, we're down at 0. By 3 pi halves, we're down at -4. And by 2 pi, we're back to 0. So there is that curve in Cartesian coordinates. So in polar curves, this is the theta axis, this is the r. This gives us a way to represent a lot of points, a lot of thetas and r's at the same time. So now we're going to graph the points r comma theta. So first, here at the origin, we start with a radius of 0 and an angle of 0. So we're at the pole. As our angle increases to pi halves, our radii steadily get larger and larger until they're at 4. 1, 2, 3, 4. So radii get larger, 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 larger until you're at 4. And as we go to pi, the radii decrease back to 0. And just to convince yourself that that's okay, think about drawing these lines. Notice how as your angle is increasing to pi, those radii are getting longer. And as you decrease back down to pi, the radii shrink again. So far, this is our curve. And it should look like a circle. It actually is a circle, and we can prove that. So the question is what happens as we go from pi to 2 pi? Okay, well, as we go from pi to 3 pi halves, the radius goes to -4. So there are all these negative radii. So all these points here, let me draw them dotted or in like a light color. So all these points here have negative radii. These points will reflect up onto those points. This point reflects there, this point reflects there, etc. So we're going to land on this part of the circle again. And similarly from 0 to 3 pi halves to 2 pi, all those are also negative radii. So all of these points reflect up onto this. So this part reflects to that part, this part reflects to that part, this part reflects to that part because of the radii being negative, and that's the trickiest bit. So your curve is the purple part only. This part that I drew here in orange is just drawing what you would see before reflection. So let's erase that since it's not actually part of our curve. Or we can't. Let's actually just white it out then. So not that. It's a tool, but actually not part of the curve. Okay. Now I said that this is actually a circle, and we can prove that. It's a little bit tricky, but here's how. So we start by observing that as r sine theta is equal to y, that implies that sine of theta is y over r. So our equation is the same thing as r equals 4 times y over r, which is the same thing as saying r squared equals 4y. And r squared is x squared plus y squared. Now that's seeming to be more circle-like. How we prove that it's a circle, we complete the square. And how we do that is we add half of this -4 squared, so add 4, and that gives us x squared plus y minus 2 squared equals 4. So it's a circle with center at the point 0, 2. There. Radius is equal to the square root of 4, or 2. And you can see that if that's my center, all the points are 2 away. And so I guess still you're not convinced that this is any fun because, well, you could graph that curve no problem in regular coordinates. All right, how about this one? The polar equation r is 1 plus cosine of theta. So first we're going to graph r as a function of theta in Cartesian coordinates. So here's theta, here's the r-axis. So since we just have cosine of theta, we go through one oscillation of cosine theta in 2 pi. Halfway's pi, then there's pi halves, and 3 pi halves. Now I'm going to start by plotting r equals cosine of theta first. So cosine of theta begins at 1, pi halves at 0, pi it's at -1, 3 pi halves we're at 0, 2 pi we're at 1. So approximately, other than the art isn't awesome, there's a graph of r equals cosine of theta. If we add 1 to it, this will just shift this graph up 1. So at 0, we'll now get 2. At pi halves, we'll now get 1. At pi, we'll be at 0. At 3 pi over 2, we'll be at 1. And 2 pi will be at 2. All right, so we start at a radius of 2 and an angle of 0. So there's our starting point. By an angle of pi halves, our radius is 1. So the radii over that time have decreased down to 1. As we get to pi, we now have a radius of 0 at an angle of pi, so things are going to decrease even more down to the origin again. By 3 pi halves, we're up at 1 again, so that whole thing has just been undone. And by 2 pi, we're back at a radius of 2 again. And from there, the cycle will repeat. These shapes are called cardioids because they look like hearts. I'm not sure if I said that right. I read too much and don't pronounce enough. But there's the picture of 1 plus cosine of theta. So this Cartesian plot lets us convert into that r theta thing, but the polar plot actually is the one where you use the radius angle definition. Let's do a couple more tricky ones. So we're going to sketch r is 1 minus 2 sine theta. So first, we're going to sketch this in Cartesian coordinates. So we have theta r. I am going to start by plotting 2 sine of theta. So that's a sine function with amplitude 2 and period 2 pi. It begins at the origin. By pi halves, we're up at 2. By pi, we're at 0. By 3 pi halves, we're at negative 2. And by 2 pi, we're at 0 again. So roughly speaking, here is the 2 sine theta curve. Now a couple things will happen. This negative will cause that curve to reflect over the theta axis in this case. So there's negative 2 sine theta equals r. And then that additional 1 will shift everybody up by 1. So that point's up here, this point's up at 3, this point's up at negative 1. So I looked at the black picture there when I should have looked at the green one. This point's up at 1, this point's now up at 3, whereas 2 pi's up at 1. Okay, so at an angle of 0, our r is 1. Angle 1, 0. These points are r theta is the order. By pi halves, so somewhere there you've crossed the theta axis, i.e. somewhere there the r was 0. Let's figure out where that is. When is r equal to 0? Well, that would mean 0 is 1 minus 2 sine theta, or in other words, sine of theta is a half. Well, that happens at the angle theta equals pi 6, and also theta equals 5 pi 6. So pi 6 corresponds to this point, 5 pi 6 corresponds to that point. So as we go towards pi 6, which is this angle, the radius goes down to 0. So back to the pole, or to the pole. Now the next part, we have negative radii, and at pi halves, the radius is negative 1. So to plot that point, we'd go up pi halves, reflect down, there's our point. Now the question is, what happens to all of the rest of the stuff? Does it go on the left or the right of those 2 dots? And the answer is it goes on this side, the left side, and here's why. These points up to pi halves are coming from this, and they're being reflected over the origin because of their negative radii. So let's just sketch them in before reflection. You see how that got reflected down onto this. And now this part that's over here, that will get reflected there. So there's the rest of that little loopy loop. And from there, the radii are all positive, so it's not nearly so bad. By pi, your radius is 1 again. So we've increased back to 1. By 3 pi halves, your radius is 3. 1, 2, 3. So getting bigger until we get to 3. and all until you get to 2 pi and it radiuses back down to 1. The fact that you have this number there will affect the fact that there's a little loopy thing in the middle. It really is because that's a negative number that this little loopy thing shows up. It is still a cardioid, it's still sort of a heart-shaped thing. So this next curve is an example of something called a rose curve. So we have the function r is 3 sine of 2 theta, and unfortunately you have to remember a little bit of how to graph sine of 2 theta. So you find the period of the sine function by taking that 2 theta and setting it to 2 pi. A normal sine function takes 2 pi to go through one cycle, so whenever the thing inside your sine is equal to 2 pi, that's how long one cycle will take. And this tells us that theta is pi, so one cycle takes pi. So by pi, we've gone through one complete oscillation of sine. So divide the interval in half, and we have pi halves, pi quarters, 3 pi quarters. And this function will begin at 0, 0. By pi quarters, we'll be up at 3. By pi halves, we'll be down at 0. By 3 pi quarters, we're down at -3, and by pi, we're back to 0. So there's one cycle, and we're going to graph this all the way to 2 pi, because that will, generally speaking, at least as far as this class goes, get you the whole curve. Okay, by 5 pi quarters, we're back up at 3. By 3 pi, we're down at 0. And by 7 pi quarters, we're down at -3. By 2 pi, back to 0. And I'm going to color coordinate what these pieces do so that you can see what maps to what on the polar graph. So first, let's look at this chunk. So the radius begins at 0 with an angle of 0. And by the time you get to pi quarters, you are the maximum distance of 3 from the origin. So 1, 2, 3, and the radii increase, increase, increase until you get to 3. And then that trend just reverses as you approach the angle of pi halves. So that produces one petal of this curve. Now the next portion, from pi halves to 3 pi quarters, is a bit tricky. Let me also label that. We have this way, and this is petal number 1, the first one that was traced. Now this part's a bit tricky because you have negative radii, so let's just worry about this 3 pi quarters point. So that is the point when you're at the angle of 3 pi quarters, but radius of -3. So we would be here, but then we would reflect down there. I'll draw the unreflected points in yellow. So all these points, those are going to get reflected over to this. And all of these points are going to get reflected over here. And so that is the direction in which that petal is traversed. And this one that I drew in yellow is actually not there. That was just used to reflect. Now from pi to 3 pi halves, by 5 pi quarters, we're at a radius of 3. So 1, 2, 3, and the radius has just been increasing that whole time, and then it goes back down to 0. So starts there, goes there, that's the third petal that's traced. And then finally, the last bit, from 3 pi halves to 2 pi, well, at this point right here, that's 7 pi quarters -3, or -3 7 pi quarters would be this point, but it's going to reflect up here because of the whole negative radius business. And these points correspond to these points, will reflect up to that part, and similarly these will go down. So there it is, your lucky 4-leaf clover. And every example that I've seen so far, if you graph the function from 0 to 2 pi, that will be at best one whole picture, like it'll give you the whole picture you need. And at worst, you're just going to be repeating some parts. So for this particular example, going from 0 to 2 pi, we got the whole picture. From that point on, we're going to start tracing this again. So first we trace the purple bit, then the blue bit, then the red bit, then the green bit. So the next one will actually be a little bit different. It turns out going from 0 to pi will be sufficient to get the whole picture. And there's a very easy pattern to determine what does this. So we're going to sketch r equals 2 cosine of 3 theta. So first we must find the period of this function. So we have 3 theta equal to 2 pi. So theta is 2 pi thirds. So by 2 pi thirds, this cosine thing has gone through one entire cycle. So here's 2 pi thirds. To figure out what's happening to cosine there, divide that angle in half. Half of 2 pi thirds is pi thirds. Half of pi thirds is a sixth. So there's 1/6. Pi thirds is 2/6. Here is 3/6. So 3 out of 6 is the same thing as pi out of 2. And cosine, well, this is 2 cosine, so cosine will begin at 2. By pi 6 be down at 0. By pi thirds be at -2. By pi halves be at 0. And by 2 pi thirds be back to 2 again. The next cycle also takes 2 pi thirds, so that will end at 4 pi thirds. Notice that halfway between those points is 3 pi thirds, or pi. And you can think the next points just count by 6. You have 1/6, 2/6, 3/6, 4/6. This point is 5/6. 6/6 is pi, 7/6. And the pattern continues. At 2 pi thirds, we would have been at 2. 5 pi 6 we're at 0. Pi we're at -2. 7 pi 6 we're at 0. And 4 pi thirds we're back up at 2. And finally, another 2 pi thirds, which gives us 6 pi thirds, or 2 pi. We get a complete cycle. Well, halfway between these will be 5 pi thirds. And we'll have 7, 6, 8, 6, 9 pi 6, or 3 pi halves, 5 pi thirds, and 11 pi 6. One thing to notice is that the number that's with the theta, that is the number of cycles in 2 pi. In the previous example, that number was a 2, and we had 2 cycles within 2 pi. In this case, that number is a 3, and we have 1, 2, 3 cycles in 2 pi. So just as a trick to help you remember that that's always true. All right, let's now graph this curve. So from 0, an angle of 0 to an angle of pi 6, the radius begins at 2, and by pi 6, you're back at 0. So there's your first little bit. Next, from pi 6 to pi thirds, by the time we get to pi thirds, we are at -2. So here's that point as a +2 gets reflected down to here. And all of these points get reflected down there. So there's the next part of our curve. And those little dots were just work. And then from pi thirds to pi halves, that's these points. Oh, these points get reflected to here. All right, next we will have the part from pi halves to 2 pi thirds. By the time you hit 2 pi thirds, which is this angle, we're back at a radius of 2. And as we approach 5 pi 6, we have a radius of 0 again. So there we go. And lastly, from 2 pi, we got that part, from 5 pi 6 to pi. By pi, we're at a radius of -2, so this point will reflect over there, and all these dots will reflect over here. So there's the next bit. And if I were to keep going and do this part from pi to 7 pi 6, well, that's going to be all of, so at pi, be this part, and that's going to reflect onto this part again. And so what we're going to do if we go all the way to 2 pi is we're just going to retrace the curve. So see if you can convince yourself to guess what a pattern is for these two examples. So the previous one we had r was 3 sine of 2 theta. There were 4 petals. And here we have r is 2 cosine of 3 theta, and there were 3 petals. And the general hint will be is if this is an even number, the number of petals is double that number. If it's an odd number, it's the same. And we also had an example that was something like 4 sine of theta. Technically, that could be thought of as a curve like this with 1 petal, which was a circle. So those are the trickiest thing. We will graph some more polar curves in the next lesson and also talk about how to do a little bit of calculus with them.